Welcome back to EGME-333 Fluid Mechanics. This video will discuss the Bernoulli equation. So let's begin by considering the fluid motion in an elementary way. If we apply Newton's second law to a fluid element in an inviscid fluid, where the sum of all forces is equal to the mass of the fluid element times its acceleration, recall that when we use the term inviscid in fluid mechanics, what we're doing is neglecting the effect of viscosity, the Greek letter mu. So in essence, there are no shear stresses tau within the fluid. Recall that the shear stress tau is given to us by the Newtonian fluid model, where the dynamic viscosity mu is where the shear stress tau is equal to the dynamic viscosity mu times the shear strain rate du dy. When the flow is inviscid, this quantity is set equal to 0. And that's because we're treating the flow as if its viscosity is equal to 0. Note that in practice, there are no inviscid fluids. All fluids have some level of viscosity. However, there are several cases in practice where flows experience small levels of strain rate, where du dy is approximately or close to 0. Therefore, the flow is experiencing a small or a negligible amount of shear stress. So when we are dealing with inviscid flows, those flows are only governed by pressure forces and gravity. So that the sum of all forces is really just the net pressure force plus the net gravitational force. The sum of those two must equal the mass of the fluid element times its acceleration. Now let's focus on the Bernoulli equation, which is given to us by the sum of the static pressure P plus the product of 1/2 times the fluid density rho times the fluid speed squared plus the product of the specific weight gamma times the vertical position z. The sum of these three quantities must remain constant along a streamline. Now, when the Bernoulli equation was derived, the following assumptions were made. Number 1, that the flow was steady. Number 2, that the flow is inviscid. And 3, that the flow is incompressible. Note that the Bernoulli equation can be applied to two different points along the streamline so that we can expand it out where we have P sub 1 plus 1/2 rho V sub 1 squared plus gamma C sub 1 on one side, and on the right-hand side, we have the quantity applied at point 2, which is P sub 2 plus 1/2 rho V sub 2 squared plus gamma times Z sub 2. And in cases when we're dealing with gases such as air, we often neglect the effect of gravity, where the Bernoulli equation reduces to the pressure P plus 1/2 rho V squared. The sum of those two is equal to a constant along the streamline. Each term in the Bernoulli equation can be interpreted as a form of pressure, where the first term is the static pressure. The second term, 1/2 rho V squared, is the dynamic pressure. And the third term, gamma Z, is the hydrostatic pressure. The sum of these three pressure quantities remain constant along a streamline, where the total sum is what we refer to as the total pressure, P sub T, and this is the quantity that remains constant along a streamline. Essentially, this concept is analogous to the conservation of energy, where the static pressure is analogous to mechanical work, the dynamic pressure is analogous to the kinetic energy, And the hydrostatic pressure is analogous to the potential energy term in the conservation of energy equation. A physical interpretation of the Bernoulli equation is that the work done on a fluid element by all forces, whether they be pressure forces or gravitational forces, the sum of those forces is equal to the change of kinetic energy of that fluid element.